Hi there. In this video, we're going to talk about the unit normal vector. Let's just say we have a scalar function of x, y, and z that is equal to some kind of constant. So the easiest way to understand something like this would be, for example, the sphere x squared plus y squared plus z squared is equal to 1. So we have an implicit function phi on the left hand side equal to some constant on the right hand side. So if we were to draw this, we draw our axes, our z, y and x planes, and we draw our sphere. Okay, it's a poorly drawn sphere, but you get the idea. Anyway, we have a point P on the sphere, and this point P is actually the position vector r. Okay, we have the position vector r, and at r we have our x, y, and z coordinates. Okay, so let's just say we are at r, and then we move a slight distance dr. So this vector r has changed by some vector, new direction, new magnitude dr. The question is, what has our function changed by? Remember, we have phi. So we want to compute what d phi is now that this vector dr has changed somewhat. Okay, and the answer to that is that d phi is actually equal to 0. If we think about this, what does this mean? Phi is actually a constant, and that constant is the radius of the sphere. If we have moved just along the along the surface of the sphere, then the radius of the sphere actually hasn't changed. So the derivative of a constant is simply equal to 0. So we saw in the last video that a differential change in a function may be represented by the gradient vector of that function. So grad of that function multiplied, or rather taking the dot product with this differential change in this other vector. So this can also be written as the gradient vector, the del operator of that function multiplied by the gradient or the differential change of the vector dr. And since this differential change in the function is equal to 0, it means that this must equal to 0 as well. And then looking at these two things, we are actually taking the dot product. So if we just remember what the dot product is, if we have two vectors, maybe a dot b, it's actually equal to the magnitude of a multiplied by the magnitude of b times cos theta. So this is actually what is happening here. So what we're saying is that the magnitude of the gradient vector multiplied by the magnitude of this differential vector times cos theta is equal to 0. What this means is that cos theta must equal to 0. So therefore, theta is equal to pi over 2. Pi over 2 is actually 90 degrees, right? So what we're saying is that this gradient vector is actually 90 degrees to this vector that has undergone a differential change. So at a point on the sphere, the gradient vector is actually pointing normal to the surface. So this is a normal vector. So the gradient vector in this instance, that's a grad. Grad of the scalar function is actually a normal vector. So if we wanted a unit normal vector, all we would have to do is divide this gradient vector by the magnitude of the gradient vector. And this is actually what the unit normal vector is. We can call it the normal vector with a hat on top. We can implement this in a simple example. So let's just take our sphere again. We can have x squared plus y squared plus z squared is equal to 1. And remember what our unit normal vector is. It's the gradient vector divided by the magnitude of the gradient vector. So what is the gradient vector? It's simply day phi day x I hat plus day phi day y j hat plus day phi day z k hat. So we can set this is equal to phi. So what that means is that this first component is just 2x, second component is 2y, and the third component is 2z. So we can compute this, for example, at the point P. Maybe P is the point 1, 1, 1. X, Y, Z coordinates of 1, 1, 1. So that means that this gradient vector at 1, 1, 1 is just 2i plus 2j plus 2k. So now we divide this by the magnitude. So the magnitude of this gradient vector is simply the square root of 2 squared plus 2 squared plus 2 squared, which is just 4 plus 4 plus 4, which is equal to the root of 12, which is just 2 root 3. So that means that our unit vector, normal unit vector, is simply equal to the magnitude, the gradient vector, which was 2 plus 2 plus 2k, divided by the magnitude, which was 2 root 3. Okay, we can see that the 2's cancel off. So what we're left with is 1 over root 3 into I hat plus j hat plus k hat. Okay, and that is our final answer.